I'd like to show you a strategy for analyzing the dynamics of a scenario, organizing the information that's available, and using it to predict how the system will move. This is going to be a bit like the guess procedure that we used in kinematics, but this will be more general and more powerful. Our objective is to construct, meaning write down and simplify piece by piece. We want to construct a mathematical model that relates the forces on an object, its interactions, to the acceleration of the object. And once written down, you can study your mathematical model to solve for unknown quantities or predict how changes to the scenario will affect the scenario. This strategy is a three-step strategy. Step one, free body diagram. You always start your problem by picking the object of interest and drawing a free body diagram for it. See the video on FBDs for guidelines on translating your scenario into an FBD that models all the significant interactions an object is experiencing at a given moment. After you've got your free body diagram, and you must start there, the most common mistake students make when getting fouled up trying to solve problems is that they skipped the FBD to try and jump right to the answer. Must start with this. Okay, then step two, AAA, align your axes with the acceleration. This step involves some freedom you have in choosing your axes. Your default XY axes are like this, but sometimes it's convenient to flip the axes. If, for example, you've got an object moving to the left and it's going to be moving left the whole time, it's convenient to make left the positive direction. So go ahead and flip your x-axis to make that the positive direction. Likewise, if you've got something moving straight downward the whole time, it might be convenient to make down the positive direction. So flip your y-axis. You get to make that choice when setting up the problem. But in addition to flipping the axes occasionally, you have more freedom with your axes. Sometimes you'll tilt them, bend them, or even rotate them as the object moves. AAA means you make your choice in order that your axes are always aligned with the direction the object is accelerating. So on a flat surface, if this pumpkin here is just going to be accelerating left or right, you want one of your axes to be aligned with that acceleration, and the x-axis is, so your standard axes work just fine. If, however, you're on an inclined plane and your pumpkin is going to be accelerating up or down that plane parallel to the plane, you want to take your normal xy axes and tilt them so that now your x-axis is aligned with the direction of the acceleration. That's AAA, aligning the x-axis with the acceleration. Now your y-axis is perpendicular to the plane, but it's no longer straight up. If you've got your pumpkin on a little wagon that you're pulling around in a circle, we'll learn later that circular motion means you've got an acceleration pointing in towards the center of the circle. So, following AAA, we want axes that stay aligned with the acceleration, meaning an axis that always points in towards the center or away from the center. We conventionally use radial and tangential axes, R and T instead of X and Y, the radial direction and the tangential direction, as in tangent to the circle. We'll learn much more about this later, but here I just want to show you that you can take your R and T axes and rotate them as you move around in the circle. At this moment, radial is pointing that way, but at this moment, radial is pointing that way. At this moment, radial is pointing that way. Keep your axes on the move so the axes stay aligned with the acceleration. If you've got your pumpkin swinging from a string, making what we call a conical pendulum, or sort of moving in a horizontal circular motion but swinging from this string, we will learn that your acceleration is toward the center of that circle. So you want an axis that's aligned with this direction. So again, we'll have our radial axis here lined up with the acceleration. And here we might call vertical the z-axis instead of y. And we might also need a third axis, three-dimensional motion here, an axis out of the page. Our tangential axis would be out of the page in this case, so RT and Z. Here, if we've got a pulley system with a rope stretched over the pulley, that means that we've got one object accelerating along the up and down the ramp here, but this pumpkin here is accelerating straight up and down. So we've got two different objects with two different axes of acceleration. Here, it's convenient to take an axis and bend it. Take the x-axis, have it point up the ramp here, but then bend it so that it points down the ramp on this side. So that over here it's aligned with the big pumpkin's acceleration, and then here it's aligned with the little pumpkin's acceleration. We can perform tricks like that to keep our axes aligned with the acceleration at all times. Once you've done that, chosen your axes to align them with the acceleration, then for every force on your free body diagram, go back to your FBD and check those forces. For every force that is not aligned with your axes, break that force into components. So let's say here, if that pumpkin on the horizontal surface was being pulled by a string this way, then there's a tension in that string. With our normal XY axes, we see the normal force and gravity are aligned with the y-axis. Friction here is aligned with the x-axis, but tension is at an angle. So tension we need to break up into components. Make it the hypotenuse of a right triangle with legs that are parallel to the axes that you've chosen. So FTX parallel to the x-axis and FTY parallel to the y-axis. Break that tension into components. Here, for the pumpkin that's on the inclined plane, let's say gravity is pulling straight down, friction pointing up, normal force that way. If we tilt our axes, then we see that friction and the normal force are aligned with our axes, but gravity is not aligned with our axes. Now gravity is the force that's at an angle. So gravity must be broken up into components. Make it the hypotenuse of a right triangle with legs that are parallel to our axes. So FGX here, x component of gravity parallel to the x-axis, and FGY here, y component of gravity parallel to the y-axis. For our pumpkin here, moving in a circular motion on a little wagon, there may be friction from the top of the wagon pushing on the pumpkin, sort of a traction, and that friction may have an inward component, making the pumpkin move in a circle. It might also have a forward component, making the pumpkin speed up if you're speeding that pumpkin up. And that way our force of friction would not be aligned with either the R and T axes, radial and tangential, so we would need to break it up into components. A radial component of friction and a tangential component of friction. For this pumpkin swinging around as a conical pendulum, that tension is not aligned with our axes. We have to break it up into components. Gravity is, however, aligned with an axis. It's fine. And then for this case, two different objects, so two different free body diagrams. Each object gets its own. For the pumpkin on the inclined plane, once again, as in this scenario up here, the force of gravity is not aligned with our tilted axes. Over on this side, however, gravity and tension are both aligned with our x-axis that has been bent and is pointing downward on this side. So no need to break either of these into components. They're aligned with the axes that we're using on this side. Note here that I've cut kind of a y-axis up that way here, and then our y-axis gets bent to kind of point off to the right over on this side. Okay, so once you've aligned your axes, find any forces that are not aligned with those axes and break them up into components. That brings us to step 3. N2L, Newton's second law. Here's where we're putting Newton's law to use. Treat the 2 or 3 axes of motion separately. So here's Newton's second law in its most general form. The net force causes the acceleration. The mass here resists acceleration. But what we want to do is use Newton's second law in component form. Treat the x direction and the y direction separately. So separate N2L for each of those directions. Then ask yourself, is the system in equilibrium along any of the axes? Is it in equilibrium in the x direction, in the y direction? Equilibrium, you recall, meaning the scales. Equilibrium as in Newton's first law of motion, static equilibrium versus dynamic equilibrium. Look at the scenario, and if you decide that the object is in equilibrium in, say, the x direction, use Newton's second law and state, here's what you will write down on the page to show your work. You'll state that the net force in the x direction is 0 and the acceleration in the x direction is 0. You're stating that you recognize the object is in equilibrium in that direction. If the object is not in equilibrium in either the x or y directions, go ahead and use Newton's second law in its full form and state both of these. Write both of these on the page. Ax equals net force in the x direction over the mass, and AY equals net force in the y direction over the mass. I usually use a little bracket like this to keep these two key equations clustered together. So you're always writing down these two to separate out the directions. Then return to your free body diagram once again and let it be your guide to expand each of these sums into a list of terms. Net force in the x direction, that just means the sum of the x components of all the forces. Net force in the y direction means sum of the y components of all the forces. So then write equals, and then this sum here equals, and then this sum there. And at this point, you'll use any other physics you know or any trigonometry that's relevant to make substitutions for some of these terms. Like, for instance, if you see a force of gravity appear somewhere, you know from the law of gravity that it can be replaced with mg. Later on, when we learn about Hooke's law for springs, you can make a substitution. When we learn about static friction, you can make a substitution. Or if you've got some trigonometry to do, say an x component of tension, you know, write that as ft sine theta or ft cos theta, depending how that angle is defined. We'll see more examples of that later. So in summary, here is our three-step strategy for dynamics. Always draw that FBD, align your axes with the acceleration, and then state Newton's second law in component form. Let's apply this last step to the several scenarios we've got right here. So this pumpkin here that's sitting on the horizontal surface, I would write for that one. Here's the N2L part. Acceleration in the x direction, net force in the x direction over the mass. In the x direction, I see I've got Ftx, the x component of tension, pulling in the positive x direction, and our force of friction in the negative x direction. So I'd write Ftx minus Ff. Those are our two forces in the x direction over the mass. In the y direction, our pumpkin is not accelerating up or down, so I know the acceleration in the y direction is 0. The sum of all forces in the y direction must be 0. I've got the normal force here plus the y component of tension, Fty, minus gravity equals 0. For this one, the pumpkin on the inclined plane. X component of the acceleration comes from summing the x components of the forces. In the x direction, I have our force of friction in the positive x direction, so plus Ff. Then I've got here the x component of gravity in the minus x direction, so minus Fgx right there over mass. In the y direction, perpendicular to the plane, our pumpkin is not floating off above the plane, and it's not sinking down into the plane. Our acceleration in the y direction is 0. So you can state that the net force in the y direction is 0. And in the y direction, we have our normal force in the positive y direction, so plus Fn, and then our y component of gravity in the negative y direction, so minus Fgy. Those must be balanced, equals 0. Here, for our pumpkin moving in a circle with our radial and tangential axes, we do the same thing. We just have radial and tangential components of Newton's second law instead of x and y components. So in our radial direction, we've got our radial component of the force of friction pointing inwards. That's our negative radial direction by our choice of definition here, so minus FFR. And then we've got the tangential component of friction pointing in the positive tangential direction, so plus FFT for the tangential direction. I got one more to show you, then I'll have you try the last one on your own. Here for our pumpkin that's being swung around in a horizontal circle or conical pendulum right here, we have a radial direction that's relevant and a z direction that's relevant. So in the radial direction, we sum the radial forces. The only thing I see is this, the radial component of tension, pointing inward in the negative radial direction. So minus FTR over the mass. In the z direction, I could improve this, because in the z direction, we see that the net force in the z direction involves the z component of tension, Ftz, and gravity in the minus z direction, so minus Fg. We can tell that those are going to be equal. Those are balanced. I can set that equal to 0 right there. That is equilibrium in the z direction. Okay. Here's what I would like you to try. Can you set up Newton's second laws for the big pumpkin and then separately for the little pumpkin. So big pumpkin gets its own set of these, and then the little pumpkin gets its own set of these. Pause the video, and I'd like you to write those out right now, including each of the terms that appears in each of these sums. Once for the big pumpkin, and then separately for the little pumpkin. Pause the video. All right, here's what we've got. Answer for the big pumpkin. In the x direction with these tilted axes here, in the x direction we should have force of tension in the positive x direction minus the x component of gravity minus Fgx, the negative x direction, over the mass. And then for the y direction, that acceleration should be 0. We're in equilibrium in the y direction, so net force in the y direction is 0. There should be normal force here minus the y component of gravity, Fn minus Fgy. Note that this is the same pretty much as this scenario up here. We just have a tension instead of a friction. For the little pumpkin, there is nothing going on in the horizontal direction, so we can just say that our acceleration in the horizontal direction is 0, net force in the horizontal direction is 0. Note that horizontal is our y direction this time because we've bent our axes all the way around. But in the x direction here, that's this direction, positive x direction points down. The sum of forces, we've got Fg plus Fg in the positive x direction minus the force of tension in the negative x direction. See how the axis has been flipped? Positive x is down, so that's plus Fg minus Ft in our sum of forces right there. There's our strategy.